Whatever allure trees might hold, they also have scads of data stored within their trunks. Daniel Griffin, an assistant professor of geography at the University of Minnesota, is here to explain how tree ring research is conducted and what kind of historical climate data he's been able to uncover in his work. I'm Dave Cantor, and this is The Best of Our Knowledge. You are Daniel Griffin, assistant professor of geography at the University of Minnesota. I'm going to start with a pretty basic question so folks can get kind of used to what we're talking about. Can you explain who Andrew E. Douglas was and then help us define dendrochronology?
Sure. So dendrochronology is a big word that in a nutshell means the study of time using tree rings. And dendrochronology is a tool for environmental science research. And so we're able to study the growth rings from trees, and we can speak more about what all that means. But it's a really powerful lens for evaluating the temporal history of environmental conditions. And because trees grow in so many places, we're able to look at those patterns across space, and then based on what we understand from science and the systems in which we work, we're able to make robust inference about processes, environmental processes, as they fluctuate across time. And so you asked who Andrew Ellicott Douglas was. A.E. Douglas is arguably the kind of grandfather, if you will, of dendrochronology in North America. Douglas was an astronomer, and he was dispatched to Arizona in the early 20th century to site an astronomical observatory, to place a telescope, to try to take advantage of the clear skies that exist in desert environments to look out into space. And so Douglas found himself in the Flagstaff, Arizona area. As he was looking for the ideal place to site his telescope, he noticed cut stumps of ponderosa pine trees and other pines and other conifers from the region, which were being logged for timber production at the time. And he noticed that the patterns of wide and narrow growth rings seemed to be highly synchronized across these fields of cut stumps and then across the area. And so, as the story goes, that was kind of where the idea came for him to begin to ask questions about what is it that it's causing these tree growth patterns to be synchronized within a stand and across the region, and what might be learned from that.
In a piece for the New York Times that you wrote called "This 500-Year-Old Tree in California Has a Big Story to Tell," you were able to reference a mega drought that ran between 1572 and 1600. So that one wasn't man-made. You were able to pinpoint it pretty specifically. So how did you figure that out, and do you know what caused it?
In tree ring dating, going back to the time of Douglas, back to the 19-teens and 20s and 30s, the tree ring records have shown these periods of extended suppressed growth. And when we see growth suppression at one tree, we might think, oh, well, maybe there was some sort of ecological disturbance, something that happened to that individual. But when we see it across individuals and across populations, and indeed across populations at the continental scale, as we now can do since we have this incredible archive of tree ring data, thousands of sites now across North America, we're able to make some inferences that there was something happening at a larger scale. And of course, we know that climate variations do occur at these large scales. For a long time, going back to the time of Douglas and the time of Hal Fritz in the 1960s and subsequent work by many of the giants at the Tree Ring Lab in Arizona, we have known about these mega drought episodes. So we're talking about drought episodes that lasted not 5 years, not 10 years, but in many cases 20 years or more. So very protracted periods of time where we had low precipitation and maybe higher temperatures. And we see these mega drought episodes very clearly in the tree rings. In the New York Times piece that I wrote, we mentioned the 16th century megadrought, which occurred in the late 1500s. Analysis that we've worked on over the last few decades shows that this was a drought episode that probably originated in Mexico and then migrated north into the American Southwest and ultimately manifest at the scale of the American West. And depending on where one is, the drought probably began in the late 1560s or maybe in the early 1570s, and it extended through the early 1590s. And so this mega drought episode it's evident in tree ring records that we collect from old growth trees. It's evident in the tree ring, it will be evident in the tree ring records that I collected earlier this week in California. So if we were to go out and sample trees that are on the timescale of 500 years old in the American West, it is quite likely that you'd see evidence for this drought episode.
The specific tree you're referencing in the Times piece, it seems like it went through a bunch of drought years. So why is this current drought any different from those from a few hundred years ago?
It's indeed the tree that we illustrated in the article for the New York Times. That's a Pseudotsuga macrocarpa, which is a big cone Douglas fir. It's a Southern California species of Douglas fir, and the growth rings from that tree go back into the early 1500s. And indeed, we see many drought episodes over that tree's life, including this protracted drought episode of the mega drought in the late 1500s. And we also see evidence for severe drought in recent decades. And indeed, when we kind of look on aggregate at all the trees that we sampled, we see that the magnitude of the drought in recent years is severe and rivals the magnitude of the drought that we see in the late 1600s. The work that I referenced in that article has been conducted by Park Williams, who is, I believe, an associate professor of geography now at UCLA. And I really admire Dr. Williams' work. He's incredibly comprehensive in his analyses. And so Park and his colleagues like Ed Cook, who championed much of this work in the early 1990s and 2000s. Ed Cook is a research professor at Lamont Doherty Earth Observatory at Columbia University. Dr. Cook and Dr. Williams and their colleagues have taken a very systematic, comprehensive look at all available data for the West, including thousands of tree ring records and thousands of observational records from rain gauges and thermometers. And it's quite clear from their work, which also incorporates information from climate models for what has happened in the past and climate model data for what we expect in the future, that the current drought episode in the American Southwest, which has been underway since about 2000 and seems to be continuing in 2022 now, is different than the drought episodes that we saw in the past. First of all, it is now that it's reached this length of 22 years, Park Williams and his colleagues have shown that it's matching the duration of the 16th century megadrought, which interestingly is one of the, there are longer megadroughts that we see earlier in the record. They also showed in a piece earlier this year that it seems to be matching the magnitude of the 16th century megadrought, if not exceeding it. And one thing that we know quite clearly now is that this drought episode is different than the droughts that we saw in the past. And this has to do with the fact that the temperatures now are higher than they've been in at least the last 1,000 years, and that's a result that's now unequivocally shown by many scientists, including the comprehensive assessment of the literature through the IPCC report. Let me try to state it a little more clearly. Drought is caused by a lack of precipitation, ultimately, and it is exacerbated by high temperatures. When the atmosphere is warm, it has greater capacity to suck moisture from the land surface and the biosphere. And so this drought seems to be unique compared to the droughts before humans had measurable impact on the climate, in that we're dealing with record high temperatures, which are directly attributable to greenhouse gas emissions. So human activities, a whole range of them, primarily the burning of fossil fuels like carbon dioxide, that release carbon dioxide into the atmosphere, causes an amplification of the greenhouse effect. Carbon dioxide and the other greenhouse gases are heat trapping. Even at their minuscule concentrations, they're able to capture the heat that's being emitted from Earth and reflect it back down. And so we're amplifying the greenhouse effect. And we have spiked the climate system by increasing greenhouse gas concentrations to a record that's higher than certainly any time in the last 1 million years, releasing these gases at a rate that's higher. We're releasing them faster than any time in at least 50 million years. And so we're causing an increased temperature to manifest across at the global scale, especially at high and mid latitudes. So the drought episode out west now is absolutely attributable to low precipitation. So we've had low snowpack, low rainfall, low snow, but it's the higher than average, the record high temperatures that drives this drought into the realm of the unusual.
Your initial interest, I guess, in the natural world, I don't know that people would necessarily connect you researching the growth of trees would connect immediately with climate change, I guess, or maybe they would. So what was your initial, I guess, interest in, like, how did you wind up studying this?
When I went to college, I didn't know what I wanted to study. I ended up in a couple of classes in the geology program based on a suggestion from a family member, and environmental geology really stuck out to me. I had the chance to spend a summer flipping burgers in Yellowstone National Park after my freshman year, and I really fell in love with the mountains and the West and decided that science of some sort would be a fun and potentially interesting way to go. In the realm of the geosciences, I never really took to hard rock geology or petroleum geology. I was more interested in contemporary societal relevance. And so I happened to find my way into a tree ring research lab and found that to be a really nice balance. Trees grow everywhere. They integrate information from their environment. It's a wonderful privilege and a joy to get to go visit places where old growth forests survive today. There's something deeply potent and powerful about being in the presence of ancient trees, whether they be big or small. And so it turns out, because we only have weather records that go back 50 years or 100 years or maybe 150 years in a few exceptional cases, trees, which grow in many, many places, have a lot of information to provide us about paleoclimate, or climate in the time before we have modern weather records. And so I really became most interested in just trying to understand the climate of the past. And the famous adage says, if you want to know where you're going, you need to understand where you've been. And so the climate system is very chaotic, and there's a lot of randomness, and it's constantly changing. And this is something that I think a lot of people understand and appreciate. If you've lived through several seasons in a given place, you understand that the weather's always changing and the climate varies. But it turns out through the science of paleoclimate, we're able to understand a lot about how climate varied in the past, where it varied in the past, and most importantly, understand why climate varied in the past. And a big takeaway from all of this work is that much of the Earth's climate variability originates in the ocean, frankly. So the El Niño Southern Oscillation is this interesting dynamic that exists in the tropical Pacific, where the ocean and the atmosphere work together to try to redistribute this intense surplus of heat and energy out to places where there's a deficit, namely towards the polar regions. And over the last 50 years, we've learned a lot about the El Nino Southern Oscillation System. And anyway, it turns out that much of the memory in Earth's climate can be traced back to the tropical Pacific. And indeed, Dave, it seems like the mega droughts of the past were almost certainly rooted in the tropical Pacific. So cold conditions in the tropical Pacific Ocean, which we refer to as a La Nina episode. These cold conditions have a connection to atmospheric circulation at the global scale. And in the mid-latitudes of North America where we live, cold conditions in the tropical Pacific more often than not translate to a change in the jet stream, especially during the winter. And the jet stream tends to have a more northerly trajectory over the Rockies, and much of, let's say, the Intermountain West of the United States is left high and dry. And so I mention all this because I think it's interesting that as we approach the winter of 2022, 2023, La Nina conditions are persisting in the tropical Pacific, and it seems like we're going to have a third straight year of cold ocean in the tropical Pacific. And so it doesn't look good for, it seems like we would expect the drought to likely continue based on this alone.
Hey, just wanted to cut in here for a second and say that if you've got any questions, comments, or even ideas for future interviews, feel free to email me at knowledge@wamc.org or send us a message on Twitter. We're at tbookknowledge. That's TBOO knowledge. Is there information or insight that you can take away from the study of old growth forests that wouldn't be available to researchers otherwise? Apart from, I guess, the climate stuff that you're just talking about.
Old growth forests are a wonderful living laboratory. Trees are these sensors of their environment. They're these organisms that preserve a record of what happened to them as individuals. And by collecting data from many individuals and many populations, we're able to learn a lot about environmental change over time. I spent most of my efforts trying to understand past climates, but a direct relation of that has to do with our ability to use tree rings and similar data sets to understand the way that climate actually drives ecosystem process and productivity. We talk about this as bottom-up productivity, and maybe the listeners will recall from their science classes this idea of the food web, or more precisely the kind of pyramid of producers and consumers. Well, it turns out that climate variability can modulate or influence primary production. And this is, of course, exactly what's happening with trees, which are autotrophs, or these are primary producers. They take the sun's energy and they convert it into useful other useful forms of energy, and that has implications all the way up the food chain. And so one of the things we've been doing lately is using data from tree rings and similar data from growth increments in marine organisms to understand the way that climate is driving what we call bottom-up ecosystem productivity. And these are things that kind of we would have always expected based on first principles to see this, but when we bring together hundreds or maybe even thousands of data sets from terrestrial and marine environments, and we see them pulsing together year by year, it allows us to fingerprint the climate system as the ultimate cause, and its climate variability as well as human modification of the climate system manifesting as climate change.
You mentioned in the New York Times story that there was a study that recreated a 12th century timeline through analyzing tree rings in the Southwest. How monumental an achievement is that? And then, since this is kind of a finite region, are there analogous works being done on other continents? Just since the development of the landscape is so radically different place to place, and like how are those then connected?
So over the last century, scientists have been collecting tree ring records across the Southwest in the United States. And indeed, that region has some of the most dense and highest quality tree ring data anywhere on Earth. And this goes back to the time of Douglas or Edmund Shulman and Hal Fritz and Jeff Dean and Tom Swetnam and Ed Cook. And it was really in the 1990s that we started to see some really impressive synthesis products and synthesis analyses that came to bear. And so I'd like to give mention to Dr. Edward Cook at Columbia University's Lamont Doherty Earth Observatory. In the 1990s, Ed Cook and Dave Miko at Arizona started to produce these synthesis products where they were able to distill hundreds or thousands of tree ring records into what they now call an atlas product, where we have these little grid cells that cover the entire region, and we have a temporal record year by year for each of those grid cells. And so this work, which we refer to as Drought Atlas, the Drought Atlas product, is the culmination, I would argue, of Ed Cook's career. And scientists like, Ed Cook's son, Ben Cook, and one of Ed Cook's longtime collaborators, now Park Williams, they're carrying this on in updating this with modern data and approaches. But it's really potent, and I think it's the culmination of a century of work that we now have this Drought Atlas product that actually covers all of North America. Going back year by year, you can look for a given place. In many places, there's data that goes back 1,000 years, and other places maybe it only goes back 400 or 500 years. The Drought Atlas effort has been now extended to many parts of the world. So Dr. Cook and his colleagues have developed Drought Atlas products for the Monsoon Asia region, for Australia and New Zealand, for a big swath of South America. We did a product focused explicitly on the greater Mexico region, and of course into Europe as well, what's known as the Old World Drought Atlas. And so one of the products that's coming online soon is kind of a globally integrated synthesis of the drought products. And I believe it's now in press. Dr. Ben Cook, who's the son of Dr. Edward Cook, has a review paper on megadroughts that takes advantage of these hot off the press products at the global scale to review the fact that megadroughts are a thing that we see in tree ring records for places that are arid or semi-arid. When I say that, I mean for dry climates, we see that severe and sustained droughts were very much a natural part of the climate process before. And as humans are continuing to pump carbon dioxide and other greenhouse gases into the atmosphere, we expect those megadrought dynamics to continue to play, but to be exacerbated by rising temperatures. So this is kind of a key point I hope your listeners might take away, is that climate has always varied. And we know a lot about where that happened, and more importantly, why it happened. We also expect those variations to continue in the coming decades and in perpetuity. And a lot of the work that's underway now is trying to understand how the natural climate variability of the past will be exacerbated by the anthropogenic climate change that's now so obvious in so many parts of the world.
Last one, I'll let you go. Is there a specific teacher that you remember having an interaction with that helped you kind of find your path in the field that you're working in now?
Thanks for that question. I've been so fortunate to have the energy and time and general investment of interest from many teachers, especially once I got to college and in graduate school. And so I'd like to mention some of those names now. So David Staley at the University of Arkansas, where I went to college and did my master's degree, really sparked my passion and interest and allowed me to see a role for myself in climate science. He's one of the, he was an author for the IPCC report back in the 90s. And by working with him at sites across the United States, I came to know the mentor for my PhD. So Connie Woodhouse is a really famous tree ring scientist in the American West. She's made incredible progress introducing tree rings and tree ring climate reconstructions and streamflow reconstructions to water managers, specifically in the upper Colorado River basin. And so she's really made incredible inroads trying to bring tree ring data into the realm of water management, which is a hot topic right now as Lake Powell is reaching unprecedented low levels. And there are big questions about how much water is in the Colorado, who should have it, how long can the previous legal precedent stand tall? Big questions now. I'd also like to give, a mention to Ed Cook and Kevin Anchikaitis, who are other heroes for me intellectually and folks with whom I've had the privilege of working with and learning from. And those are just a few names, but I think it's also worth noting that there seems to be a growing number of folks that are using tree rings to understand environmental systems. And there are many giants in the field like Lisa Gromlich and Hal Fritz and Tom Swetnam and many others whose names are escaping me. And I'm trained, also I should mention, I'm trained in the American school. There are incredible scientists from Europe who I'm leaving out here. But there are also a great many folks in my cohort and in younger generations who are interested to try to understand the environment and what humans are doing to them. And I think that tree rings are an incredible gateway for understanding environmental systems. And one of the things we're hoping to do is leverage this powerful approach. I mean, trees, even my young elementary age daughters understand that trees form a ring per year and that we can understand something from their environmental records. And so I think there's a great untapped potential to harness tree rings as an accessible gateway for environmental systems thinking. And there are a lot of early career scientists doing incredible, inspiring work. And I'm excited to see where this goes over the next decade or three.
That's all we've got for this edition of the show. I'm the host and producer of The Best of Our Knowledge, Dave Cantor, and our theme music this and every week is a track called Musical Chairs by LA producer Omid Valizadeh. A link to his SoundCloud page is in the show notes. You can find The Best of Our Knowledge online at WAMC.org and on just about any app you can think of: Apple Podcasts, Spotify, and Pocket Casts. So go ahead, subscribe, and join us next week for another edition of The Best of Our Knowledge.